We're in Rosen, section 9.1 on relations and their properties. We're going to go through 4 properties that relations may or may not have. And to do this, we'll use examples from earlier in the slide deck of the 6 relations. The first property is called the reflexive property. So if R is a relation on A, that is from A to A, we say that it's reflexive if and only if AA is an element of R for every element A in the set A. We can represent this symbolically. For every X element of A implies XX is an element of the relation. All right, let's take a look at our example relations from earlier and see which ones are reflexive. If for the ones we looked at earlier, relation 1, 3, and 4 are reflexive because each one of these has the property for every X element of A implies XX is an element of R. A is less than or equal to A is equal to A, and here A is equal to A. The other relations are not reflexive, and to show something is not reflexive, all you need to do is find a counterexample. No number is strictly greater than itself. Here, 3 is not greater than 3 for relation 2. Relation 5 is not reflexive because no number is equal to itself plus 1. Here the example is 3 is not equal to 3 plus 1. And not every pair of numbers added together is less than 3, so this relation is not reflexive either. So one more point, if A is the empty set, then it will have the empty relation, and it is reflexive vacuously because if A is the empty set, the hypothesis of the definition is always false, meaning the implication is always true. So just a curiosity when A is the empty set. Okay, the next property that a relation can have is called symmetry. And we say that a relation R on A or from A to A is symmetric if and only if when that BA is an element of R whenever AB is an element of R for all pairs of elements in A. And they don't have to be distinct. You could have AA as well. Here it is symbolically for every X and for every Y. X, Y, and R implies YX is in R. All right, from our 6 relations earlier, the relations 3, 4, and 6 are symmetric because if A is equal to B, then B is equal to A. That's for relation 3. Same for relation 4. And if A plus B is less than 3, then B plus A is less than 3. So 3, 4, and 6 relations from earlier are symmetric. The other relations are not symmetric, and we'll look at their counterexamples. For relation 1, note that 3 is less than or equal to 4, but 4 is not less than or equal to 3, so it is not symmetric. Similarly, for relation 2, 4 is greater than 3, but 3 is not greater than 4, so it is not symmetric. And for 5, 4 is equal to 3 plus 1, but 3 is not equal to 4 plus 1, so it is not symmetric. The third property we'll discuss is antisymmetry. So a relation R on set A is called antisymmetric if for all pairs of elements in A, AB in the relation and BA in the relation implies that A is equal to B. Here it is symbolically for every X for every Y, XY in R and YX in R implies X and Y are the same element. And here are the relations from earlier that are antisymmetric. Relation 1, if A is less than or equal to B and B is less than or equal to A, then then A must equal to B. Similarly, if A equals B and B equals A, then A equals B. These other two are, here's a little build. Again, for any integer, if A is less than or equal to B and B is less than or equal to A, then they must be equal. Note that for relation 2 and relation 5, they will be true vacuously because no pairwise elements ever satisfy the hypothesis. No pair of elements for no pair of elements is it true that A is greater than B and B is greater than A, and for no pair of elements is it true that A equal B plus 1 and B equal A plus 1. So relation 2 and relation 5 are antisymmetric vacuously. Which relations are not antisymmetric? Relation 3 and relation 6, we'll look at their counterexamples. Basically, we have to find a pair of elements that xy and yx are in R, but y not equal to x. So 1 and -1 and -1 and 1 belong to R3, but clearly they are not equal to each other. And for R6, 1 and 2 belong, and 2 and 1 belong, and 1 clearly does not equal to 2. All right, so that's reflexivity, symmetry, antisymmetry, and the last one is transitivity. So here we have a relation R on A. We say that it's transitive if whenever AB is in R and BC is in R, then AC is in R for all triplets in the underlying set. Symbolically, it's going to be a for every x, for every y, and for every z, xy in R and yz in R implies xz is in R. So we can see that these are the same, and then we look to see if the outer two form a pair in R. All right, which relations are transitive that we saw earlier? 1, 2, 3, and 4. The less than or equal to relation, I have a build for that. If A is less than or equal to B and B is less than or equal to C, then A is going to be less than or equal to C. So R1 is transitive. That'll be a similar argument for 2. And of course, equality carries the transitivity property. For non-transitive sets or relations, R5, A equal B plus 1. Note that 4, 3 and 3, 2 are in the relation. They have 3 here, but 4, 2 would be in the relation if it is transitive, and of course 4 does not equal to 2 plus 1. Similarly, 2, 1 and 1, 2 are in the relation for R6. In that case, we would expect 2, 2 to be in the relation if it was transitive, but 2 plus 2 does not equal to 3, so it is not transitive. And that's a discussion of 4 important properties that relations on sets can have: reflexivity, symmetry, antisymmetry, and transitivity.